Welcome to the second in this series of videos, and in this video we're going to be looking at question 3. Question 3 asks you to explain what's meant by the term phenotype. Now I'd hope that everyone would know that the phenotype was the physical characteristic or the physical features of an organism. However, this was a 2-mark question, so something that you had to say that went a little bit beyond that. This is the full answer that we were looking for. In addition to saying that the phenotype was the physical characteristic of an organism, you had to explain that the phenotype could be due to the organism's genes or due to its environment. So don't forget that second part that I put in red there. If you get a similar question in the future that asks you a question like this, remember that the examiners might want both parts of that answer. Moving on, we have a question that has a family tree. This is what you can call a pedigree analysis type question. And it tells us that Tay-Sachs disease is a human inherited disorder, and it tells us that sufferers of this disease often die during childhood. It then tells us that the allele for Tay-Sachs disease, T, is recessive to the allele capital T. So this is the first key piece of information for this question. This is the first key piece of information we've got, and it tells us that the allele which causes the disease is recessive. It then gives us a family tree. Now whenever you get a family tree like that, the first thing that I'd want to do is add on as much information as I possibly could. The first thing that I've put on up here is I've added on a little table showing me what the relationship is between the phenotypes and genotypes of the individuals here. And from the information that they've told me, I know that capital T, that genotype would be that would produce a normal phenotype. Little t would be someone who suffers from the disease, and capital T would be someone who's a carrier from the disease. If I look at my family tree here, I can see that there seem to be both males and females affected from the disease. So that probably suggests that this is not a sex-linked disease. So I'm probably correct in representing it with T's, big T's and little t's, rather than using X's and Y's. Now once I've got this far, what I can then do is I can go on and I can add the genotypes to my family tree. Affected individuals, as in the individuals who actually have Tay-Sachs disease, are shaded in on the family tree, and I know that their genotype must be little t. So I'm going to put that onto my family tree. So you can see from this that individuals 1, 9 and 11 must have the little t genotype. Now individuals 3 and 4 here are not affected by the disease, but they have produced affected offspring. Now that tells me that individuals 3 and 4 must be carriers of this recessive allele. Otherwise, it wouldn't be possible for individuals 9 and 11 to have inherited 2 copies of that recessive allele. So I can deduce from that 3 and 4 must have the genotype big T, little t, the heterozygous genotype. The actual question that goes along with this pedigree chart asks us to explain one piece of evidence which proves that the allele for Tay-Sachs disease is recessive. Now for any question like this that asks us for the evidence that a gene or an allele is recessive, what we're looking for is a situation where 2 parents with one kind of phenotype produce offspring with a different kind of phenotype. And that's exactly what we've got in individuals 3 and 4. They have an unaffected phenotype, but they produce children with an affected phenotype, children who do have the disease. So if we can explain that, we'll have explained the evidence from the diagram that shows that this allele for the disease must be recessive. This is the answer we should have, and it says that individuals 3 and 4 do not suffer from the disease, but produce offspring with the disease, and that's only possible if the allele for disease is recessive, and if individuals 3 and 4 are both carriers of the recessive allele. For a question like this, you need to both explain that the parents have produced offspring with a different phenotype, but you also need to mention that the parents are heterozygous or carriers of the recessive allele for that second point. Moving on, we've got a harder question that asks us to explain one piece of evidence in the diagram which proves that the allele for Tay-Sachs disease is not on the X chromosome. Now these questions are a bit harder than the questions that ask us to explain the evidence that something is recessive. I think the best way to answer these questions is to go back to our diagram and try and imagine what the diagram would be like and what the implications would be if this allele was on the X chromosome, and hopefully we'll come up with something that is simply impossible, and we can use that as evidence for why this allele must not be on the X chromosome. So here's our family tree again, and what we're going to do is we're going to get rid of this, And we're going to imagine a different version of this where the allele was on the X chromosome. Now if this allele was on the X chromosome, we'd have the following genotypes related to each phenotype. An individual who was female and didn't suffer from the disease would have an X big T genotype. A female carrier of the allele wouldn't be affected by the disease, but a carrier of the allele would have to have the X big T X little t genotype. And in the unlikely event that there was a female sufferer, that female would have an X little t genotype. For a male, there's only two options. A male can either be X capital T Y, in which case they'd be normal, or X lowercase t y, in which case they'd be a sufferer from the disease. So, once we've worked out what the genotypes would be like if this were an X-linked disease, we can do the same thing we did last time, and we can go onto this chart and we can start to fill in some of the genotypes. Now it's normally easiest to do the sufferers, or the people with the recessive genotypes, first on these kind of charts, because they're the easiest to work out. We know that all the affected individuals must just have X little t chromosomes, or X little t and Y chromosomes. So our two affected males have an X little t Y genotype, and the affected female, individual 11, has an X little t genotype. Now, what we can then ask is whether this is actually possible given the phenotypes of the other individuals in this family tree. The most helpful individual here is individual 11, because individual 11 must have those two X chromosomes with the recessive allele. Now that means that individual 11 must have received one X chromosome with the recessive allele from both individual 3 and individual 4. That means that both individual 3 and 4 must have an X little t chromosome. That means that the genotype of individual 4 must be X little t, X big T, because individual 4 is not affected by the disease. So that seems reasonable enough, that's possible. However, what this then suggests is that if individual 11 is a sufferer from the disease, individual 3, this person's father, must also have had an X little t allele. That would suggest that individual 3 has this genotype, X little t y. Now that's not possible as a genotype for individual 3, because individual 3 does not suffer from the disease, and if this person had an X little t y genotype, then they would suffer from the disease. So we've got a contradiction there, and the contradiction is that individual 11 is a sufferer from the disease, who would have to have an X little t genotype if this were an X-linked allele, and that wouldn't be possible with an unaffected father, because the unaffected father could not have an X little t chromosome. So I hope you're able to follow the logic there. I think these questions are a lot harder than the questions that ask you to explain the evidence that something is recessive. Here is the answer that we would be looking for then. In words, we would say something like this. If the allele was on the X chromosome, that would mean that individual 11 would have to have an X little t genotype. And that means that individual 11 would have had to have inherited an X chromosome with a recessive allele, the X little t chromosome, from both parents, 3 and 4. However, individual 3 is not affected by the disease, so cannot have an X chromosome with the recessive allele. And that's because for an X-linked disease, you can't have carriers, or you can't have male carriers at least. You can only have male sufferers and male individuals who don't have the recessive condition. Following that question, we've got a Hardy-Weinberg question. So, with any question that's about the Hardy-Weinberg theory, or the Hardy-Weinberg question, the key thing is that you read the information you're given carefully and work out which of the numbers and which of the bits of information in the question relates to which part of your equation. Now in this question it tells us that in a human population, 1 in every 1,000 children born had Tay-Sachs disease. Now that's telling us something important. We know that the sufferers, the people who actually have Tay-Sachs disease, have a little t genotype, the homozygous recessive genotype, and that corresponds to the Q² term of our Hardy-Weinberg equation. Now it tells us that 1 in every 1,000 children born has Tay-Sachs disease, so that's telling us that that Q² is equal to 1 over 1,000, or 0.001. Now the question's asking us to calculate the percentage of the population that we'd expect to be heterozygous for this gene. Now The heterozygous proportion, or the proportion of people who are heterozygous in the population, corresponds to the 2pq term in our Hardy-Weinberg equation. So what we've got to calculate in the end is what 2pq is equal to. So let's put that next to the space for the answer. So we know what q squared is, and we've got to get to 2pq. So all we've got to do is get from one to the other. Now, we need q in order to work out 2pq, so a sensible first step will be working out what q is. And in order to do that, we need to square root q squared. So if we square root q squared, in other words, we take the square root of 0.001, we get an answer of 0.0316. There are more decimal places to that answer, but I've just recorded it to 4 decimal places there, so that I minimise the chance of any rounding errors. If I'm going to calculate 2pq, I also need p. So I need to work out the value of p. Luckily, I've got the first Hardy-Weinberg equation, the one that tells me that p plus q equals 1, and I can use that to work out p if I know q. So I'm going to use this expression down here. I'm going to say that 1 minus q is equal to p, and that means that 1 minus our previous answer for q, or 1 minus 0.0316, is equal to 0.9684. And again, I've recorded that to 4 decimal places to avoid any rounding errors. So to finish this off, I need to calculate 2pq, and I'm going to take 2 and times that by q, which is 0.0316, and p, which is 0.9684, and I get an answer of 0.0612. I've got to be careful though, because this question is asking me to calculate the percentage of the population that I'd expect to be heterozygous for that gene, and I've got a percentage sign after my answer to remind me of that fact. So to convert that final answer into a percentage, I need to times that by 100. The final answer I get is 6.12%. I'd normally give my answers in an exam of this type to 2 decimal places, but there's no marks for it for giving answers to a particular number of decimal places. The examiners were willing to give any answer between 5.8 and 6.2, and that's to be kind to people who may have rounded their numbers slightly differently to me. So for these kind of questions, you don't need to worry about using the exact numbers on your calculator to all the number of decimal places your calculator shows. You can do a bit of rounding and you won't be penalised for that. The final question tells us that the actual percentage of heterozygotes is likely to be lower in future generations than the answer to part Ci, and it asks us to explain why. Now, we've used the Hardy-Weinberg equation to calculate that answer of 6.12%. The Hardy-Weinberg theory and the equations that go with it rely on certain assumptions. They rely, for instance, on non-random mating, and they assume that there's no immigration or emigration out of a population. One of the other things that the Hardy-Weinberg theory assumes is that genotypes all have an equal chance of survival and an equal chance of reproducing. So in other words, it doesn't matter what your genotype is, you have an equal chance of living long enough to reproduce. Now for this particular gene, that doesn't seem to be true. If you've got the little t genotype, you're going to suffer from Tay-Sachs disease. And way back in the stem of the question it told us that individuals with Tay-Sachs disease are unlikely to survive into adulthood and be able to reproduce. So as a result of that, the assumptions of the Hardy-Weinberg theory are not met. Our answer should be something like this. We should say that individuals with a TT genotype, or a little t genotype to be precise, are less likely to survive long enough to reproduce compared to individuals with other genotypes. And as a result, we're going to have a lower percentage than 6.12 in future generations.